Hey guys, welcome to this video on this graphing question from the 2020 exam. We're looking at some relationships between the function, the first derivative and the second derivative, and this is quite a challenging question. So I'm going to go through this one here. So let's have a read. We've got figure 6 shows the graphs of f of x and g of x between 0 and 7. So f of x is this one here and g of x is this one here. That's labelled for us. The graph of each function has exactly one stationary point located at x is 2. State the nature of the stationary point for f of x when x is 2. So here's f of x. The stationary point of f of x is this one here. It's going to be a local minimum. Okay, so nature just means what is it? Is it a local minimum? Is it a local maximum? Or is it a stationary inflection? Here we've got the sign diagram for the second derivative of g of x. That means this is the sign diagram of g dash dash of x. Now remember, what that tells us is when g of x has points of inflection. So we can see there's a point of inflection at x is 2, and so it changes from being concave down to concave up. And then there's another point of inflection at x is 6. And so there, between 2 and 6, it's concave up. And then after 6, it's going to be concave down. All right, that's told us by these values here. State the nature of the point that is located at x is 2 on the graph g of x. Well, what we can see is it's increasing, it goes horizontal, and then it keeps increasing. If we were to draw a sign diagram of the graph of g dash of x, it's going to look like this. Okay, that it is g of x is increasing until we get to 2, and then it keeps increasing, and it's got positive slope for its entire duration. So that's what the sign diagram of g dash of x will look like, which means what we have here is stationary inflection. All right, it changes from being concave down to concave up, and we can see it's horizontal at that point, so it's stationary. So we have a stationary point of inflection. The graph of y equals f of x in figure 6 has one point of inflection at x is 5. All right, so on the graph, f of x has a point of inflection at x is 5. So we can see f of x is concave up until we get to there, and then it's going to change into be concave down. Determine the intervals for which f dash of x is increasing. Okay, so make sure you read that carefully. When is f dash of x increasing? Well, what we're going to do is we're going to draw, so remember you've got f of x, and f dash of x tells you the rate of change of f of x. So when f dash of x is positive, it means f of x is increasing. When f dash of x is negative, it means f of x is decreasing. Similarly, if we have the second derivative of f of x, so f dash dash of x, all right, this is the rate of change of f dash of x. And so when f dash dash of x is positive, it means f dash of x is increasing. And when f dash dash of x is negative, it means f dash of x is decreasing. So we're asked, when is f dash of x increasing? Well, what we're going to do is we're going to draw the sign diagram for the second derivative of f of x. I think this is the best way to do it. And all we have to do there is say, when is it concave up and when is it concave down? We can see that f of x is concave up until we get to 5. So I'm going to draw a sign diagram here. It's concave up until we get to 5, and then it is concave down. All right, that's our sign diagram of f dash of x. We're told this piece of information right here. And so then we're just pointing out that relationship. This here describes the rate of change of f dash of x. All right, and so this is going to tell us when f dash of x is increasing. Increasing for 0 is less than x is less than 5. Increasing over that interval. Okay, let's move on to D. So ticks which statement is true. So we're looking at just between x is 0 and 2. And we've got the three statements here. F dash of x is less than g dash of x. F dash of x equals g dash of x, or f dash of x is greater than g dash of x. What do they mean? Okay, this one's saying between 0 and 2, the slope of f of x is less than the slope of g of x. Here it's saying the slope of f of x and the slope of g of x are the same. And this one's saying the slope of f of x is larger than the slope of g of x. Well, let's have a look. F of x has negative slope until you get to this point here. Remember, we're only talking about between 0 and 2. And so we can see f of x has negative slope and g of x has positive slope. So g of x is increasing, f of x is decreasing. That means the slope of g of x is larger because it's positive. It has positive slope, f of x has negative slope. So that's the one we're going to tick, the one that corresponds with that. So that is, g of x has a larger slope than f of x. So f dash of x is less than g dash of x. Same again, between 0 and 2, which statement is true? This time we're talking about the second derivative. Now remember, the second derivative tells us when's it going to be concave up and when's it going to be concave down. And what we can see is between 0 and 2, f of x is concave up, all right, which means the second derivative of f of x is positive, and g of x is concave down, all right, which means the second derivative of g of x is negative. So the statement that we're going to tick here that's going to be correct is that the second derivative of f of x is larger than the second derivative of g of x, okay? Because f of x is concave up, so the second derivative is positive. G of x is concave down, so the second derivative is negative. Okay, now we're talking about between 2 and 7. So we're not talking about between 0 and 2. We're talking about between 2 and 7. And we're told, given that the value of f of x take g of x is increasing. So just what that statement means is as you move across this function, the space between them gets larger and larger and larger. As x increases, the gap between them gets larger and larger and larger. And what that means for us is the slope of f of x is steeper than the slope of g of x. The slope of f of x is larger because it's getting further and further apart, okay? If they were getting closer and closer together, it would suggest g of x is larger because it's getting closer to f of x. But because they're getting further apart, it suggests that the top function has a larger slope. And so that's going to help us answer this one, is that the slope of f of x is greater than the slope of g of x over this region because the distance between them is increasing. Okay, on the axes below, sketch a graph of g dash of x between 0 and 7. Now, the first thing is we've got our sign diagram here of g dash of x. Okay, we use that for this step here. And what we can see is that g of x is increasing until we get to 2, and then it keeps increasing. So what that means is it's going to be positive. Okay, it's going to be positive, and then it's going to touch at 2, and then it's going to still be positive. All right, it's still going to be positive. And it has to be, we'll just do that point there for now. It has to be under f dash of x. Okay, it has to be under this curve because of this statement here, that the f dash of x is larger than g dash of x. All right, and so because g dash of x is underneath it, it's going to satisfy that truth, that this value, the y value of this function, is larger than the y value of this function. It's underneath it, so it satisfies that truth. Okay, so this is a 3-mark question. You're getting 1 mark for this part. You're getting 1 mark for recognizing that it's beneath. There's 1 more mark that's a bit harder to see. Now we learned, when we're talking about f of x, f dash of x, and f dash dash of x, that point of inflection on f of x corresponds with a turning point on f dash of x, corresponds with a root on f dash dash of x. So down here, let's make that connection again. We've got this point of inflection, okay, because it's a root on the second derivative. It's going to be a point of inflection on the first function. And remember, a point of inflection on f of x corresponds with a turning point on f dash of x. So if we have a point of inflection at 2, we've got the turning point at 2, that's the local min. If we have a point of inflection at 6, it means we need another turning point at x is 6. And it's going to be a local maximum. And the reason is, all right, what's happening is the slope is steepest at that point, and then the slope starts getting less, okay? It transitions from being concave up to concave down. And so the slope transitions from, it's still positive slope, all right, and it's still increasing, but the rate at which it increases starts to decrease, all right? You see there it changes from being concave up to concave down. And so along that point, what we have, remember, this is the slope. This describes the slope of it. And so the slope reaches its steepest point. Point of inflection is always going to be, as long as it's a non-stationary point of inflection, is always going to be the steepest point where the slope is steepest. And so if this is the slope function, this is where the slope is steepest, and then it becomes less steep. All right, that's it, transitioning from being concave up to concave down. So you get, and between 2 and 7, g dash of x is always less than f of x. Okay, so you get, 1 mark for there, 1 mark for recognizing it needs to be below f dash of x, and then 1 mark for that turning point. So this is quite a tricky question, and I hope we can sort of wrap our heads around it. It's one of the harder graphing problems I've seen, but it is a good one, so I recommend you tackle it and understand the concepts that are going on here.